Good evening, everyone. My name is Michael Goss. I'm Chairman of the Civil Division here in Engineers Ireland. We can just start now. This evening's presentation is on developments in integrated track design. Just before we start, can I just ask you to put your phones on silent, and could you just note the fire exit doors in the corners of the room as well. This presentation is being co-hosted this evening with the the Engineers Ireland Civil Division, the Institute of Civil Engineers, Republic of Ireland branch, and Engineers Ireland Railway Group. The presentation would outline recent developments in various rail track systems used in Dublin and across Europe for light rail and metro systems. It gives me great pleasure to introduce tonight's speaker, Marcello Corsi, who's a chartered engineer and leads the track design department of Transport Infrastructure Ireland. He is a member of the panel of EU railway experts evaluating research projects for the Shift to Rail programme, and he was awarded Chartered Engineer of the Year 2016 for his international research and innovation approach in light rail track systems. The presentation should be about 45 minutes, maybe 50. Marcello will be happy to then take questions afterwards, so if you could hold off to the very end for questions. So could you just welcome Marcello, please? Thank you very much.
So thank you, everybody. Good evening. Thanks for being here at 6:30. Actually, I hoped to be quick and interesting with the presentation. Although I tried to keep it quite low and from the technical point of view, I wouldn't go so much into the details. So my name is Marcello Corsi, as I was introduced, and I'm responsible for track design, track and alignment design in Transport Infrastructure Ireland, where I've been working for the last 9 years. It used to be RPA before, and then TII after the merger with the NRA. What I'll go through tonight, it's mostly about the various track types used in urban field for light rail and metro, mostly light rail. And then I will spend a bit more time on the embedded track, which is probably the most tricky part of our job. Let's have a first look at what are the track functions and the key components, first of all. I have there a picture of a normal, traditional ballast track. So the track has to support the vehicle, guiding the tramway or the trains and moving it. So when I say supporting, it's mostly vertical forces that are there anyway. So that those are mainly the axle load of the vehicle. Guiding would be through the curves. There are lateral forces that come into the play. But there would be lateral forces also on a straight alignment because of the nosing of the vehicle, the particular way a railway vehicle negotiates the infrastructure. And then moving, meaning the acceleration and braking forces. So those are mostly longitudinal forces. They need to be transferred from the wheel to rail contact into the infrastructure through several components of the track. Now, depending on the track systems, those would take different forms, but there are some key aspects that are common to all the track systems. We also need to provide a smooth surface for running the vehicle with as little as possible friction. That's the secret of the low energy consumption of railway systems. Reducing vertical and tangential forces, provide a good drainage, stress distribution, and then, typical for any civil design probably, ease of construction, reduce life cycle cost, the durability of the infrastructure. But they are very important for light rail and for railways in general, because also the maintenance becomes critical in terms of the windows available for track replacement or maintenance in the night times. Those are the three forces I was speaking about, and you can see on the bottom right part a picture taken at the wheel to rail interaction. While going into the key components, I'd say we have the rails, which are the two guiding and supporting elements that are interfacing with the wheels. Then we have a fastening systems that link the rails to sleepers or to a slab track, depending on the system itself. We'll see it later. Sleepers, which are then transferring the load into the ballast bed, sub-ballast and subgrade. The function of the various layers there is to distribute the loads and to spread the loads onto the ground. let's go into the key track components, the two rail types that we use in light rail. One is the groove rail that you see on the left hand side, and it's mostly used for embedded track, so meaning when the track is flush with the road components. And the groove and the keeper, which is the narrow part of the groove there, it's not meant to do anything other than providing a flangeway, so creating the flangeway for the flange of the wheel, so keeping asphalt or whatever the finish aspect is away from the flangeway. While the other rail is a typical Vignol rail that is used for open track systems. The bottom part, as you see, is a transition rail, just to have a smooth transition between the two rail profiles, that the wheel doesn't feel any difference passing from one to the next. And then on the bottom right, you can see a typical fastening system with springs and the bolts getting into the sleepers, and the sleeper pad, which is the first resilient material that we have below the rail. The rails work as a beam, especially because they were born to be discretely supported on sleepers. So the shape of the rail comes from a beam itself, and then the top part of the rail is designed to interface correctly with the wheel profile. In terms of track types, we have a big group of track types in light rail, much bigger than what you would see for heavy rail, and that's why our job in light rail is very interesting. It's differentiated. We have segregated tracks going from ballast, slab, green, plinth, and direct fixing, all based on the use of the Vignol rail, and that's how the wheel will interface with the rail itself. And then embedded track, which is with a groove rail, shared or segregated. This is probably a bit more detailed view of how the axle sits on top of the two rail types. Let's start with the ballast track. I'll fly over some of them because they are quite traditional, well known. This is a picture taken at the moment in Luas Cross City in the Cabra area. It's the construction of the ballast track there. This is my favorite track type. The problem is we can't use it everywhere. I would have used it in O'Connell Street if it was possible to do that. But for obvious reason, you can't use this track type everywhere. Although we have been using this on, for example, this is a complex junction in Red Cow. It's quite a flexible track type. We have been using it on line B1, this is the Luas, just along the footpath. So there is a perception out there that ballast track can't merge well with the urban landscape and realm. My opinion is different, but again, it's a question of opinion. What are the pros and cons of ballast track? I'd say the cost is a big plus. The ballast track is far the cheapest, about €1,000 per linear meter of track. From a maintenance point of view, for light rail in particular, is a very low maintenance cost because the design is quite similar to the heavy rail, but our axle load is very light, so we are about 10 ton per axle, while heavy rail would go up to 25, 27. So that meaning that the forces that we transfer to the ballast track are much reduced, therefore our life of ballast track would be much longer. We need less stamping, which is the activity with which we reline and re-level the track. So if you take out the tamping, the ballast track is very easy to maintain. It's self-draining. It provides very flexible track itself, because if you want to reduce, for example, cant as a consequence of speed restrictions, you can always do it. Visually speaking, it's not the worst track type. Noise-wise, is the second best, I'd say, after the grass track. And in terms of drainage, snow, derailment containment it's all performing very well. Those are the benefits of the ballast track, the construction cost and the ease of maintenance, I'd say. In terms of rail replacement, it's very easy. You can unclip the rail and just replace long sections of rail in one night. Slab track is slightly different in that it's similar to the ballast track, but the ballast is replaced with a slab, a concrete slab, and you could have continuous sleepers or B-block sleepers embedded in the slab itself. It's generally built as a top-down technology, whereas we hold the rails and the sleepers from the top with horses or jigs, and then you pour the slab below, and the slab will embed all the system. This is what we have on Luas in 2004. So the original Luas lines were built on the base of this Edilon system with a double resilience layer. So there is a resilient pad under the rail, and then we can see the second resilience layer below the blocks. It was just to limit vibration and attenuate the ground-borne noise, although it only works with some frequencies higher than a certain level, because I'd say to mitigate lower frequencies, we need to deal with a floating system which has a much bigger mass than this one. This is the Luas 2010 line A1, another type of slab track, very similar from the visual aspect, only one resilience layer, so probably was less vibration, I'd say was less dealing with low frequency vibration, but at the same time it had a continuous leaper supporting the rails. So we wouldn't have any kind of issue with this track system in terms of gauge control, which is the distance between the rails. While I have to say that with the previous system, we had some issues during the lifetime. We're still having some maintenance issues, which we are dealing with, because the blocks are independent. So if you get one block free, the risk is to lose the gauge control, which we are on top of it now at the moment. That's why we introduced a full sleeper in the slab track. This is the slab track we're building for Luas Cross City, very similar to the previous one that you have seen. Continuous B-block sleepers in this case. Plinth track is a direct fixation, and we mostly use it on bridges. The reason being that the plinths provide an efficient derailment containment system. And on top of that, the height of the plinths can compensate between the different tolerances in construction levels, between the civil tolerances of the bridge and the quite tight tolerance of the rail construction. So we can regulate the levels with the plinths. Direct fixation, this is one kind of direct fixation, which is the Voslo 336 system. Grass track, this is the Luas, which you can see more than a grass track. The cross section, the next slide, is an embedded track really, based on groove rails with concrete shoulders, upstands around the rails, and then pockets of grass with a significant amount of reinforcement and drainage system there. We were looking around Europe and the way it is done, and we retrofitted a section of slab track on Luas A1 as a test only, which is a much easier way of providing grass track. So really, it's an open slab track, as you can see the track adjacent. We only retrofitted one rail to see how it looked like, with recycled rubber fillers, chambers around the rails to keep the grass away. Then drainage layer, geotextile, and grass on top. And that's the cross section actually there. There are different ways of building grass track anyway. Let's go now to the embedded track, which is the key, I suppose, of my presentation tonight, and is the track that mostly you'll see around the city for light rail. This is Arcor Street for the Green Line. Different finishes, different ways of building it, and we'll see across Europe how many different standards are applied. Actually, there are no real standards for light rail track, and that's the challenge we are facing every day. In this case, this is Talla Terminus on the red line. You can see the different finishes, granite sets on the bottom part, imprinted concrete up there, and then the scissor crossover of the terminus there. Again, this is the Luas B1, 4 different finishes, the terrain paving there, asphalt in the middle for the road crossing, an imprinted concrete for pedestrian crossing, and again the terrain pavement before getting into the ballast track. So it's a very flexible system of track in terms of finishes. The architects love it. From an engineering point of view, it's much more challenging. It's difficult for the maintenance. It's very expensive to build. Let's see, those are really the pros and cons. I mean, pros, very limited pros. It's just that it's the only way you can go across the city. While in terms of cons, I'd say the rail wear is an issue. Maintenance, rail replacement, get the rail free to take it out in night shifts is a big challenge. Tighter construction tolerances, because we need to limit the wear, and at the same time we need to match the existing threshold levels on the roads. And it's a road and track design at the same time. Therefore, the joint interface of the rail with the road is a particular challenge for railway engineers. The keeper is another issue. Because of the groove rail, we risk to get into what we call back flange contact. If there is a wear on the guiding rail, the wheel set will move across and will get into the back flange contact of the other wheel on the keeper, which is something to avoid as much as possible. So tighter maintenance tolerances as well. And the vertical design, I mentioned that the cost is up to 3 times the cost of ballast track. So we can get to 3,000 euros per linear meter, depending on the finishes. This is the embedded track that we built for the Luas in 2004. 2 rails, completely independent one of each other, a double layer of reinforcement for a 2-stage slab. The rails are encapsulated into a proprietary ALH rubber resilience profile. So they came on site factory coated into this material. And you can see the bottom in the center. When the finishes are different from concrete, we used to have two shoulders, concrete upstands around the rail, which had different functions. One of them would be to delineate the responsibility of maintenance between the track and the road, and also to have a clear line between of support of the flexible fillers of the road. At the same time, the low level of reinforcement of those shoulders would prove to be challenging in the future, and we'll see what I mean by that. 2009, the embedded track was built slightly different, but the two shoulders are still there. The rail is still encapsulated with a different material now. We'll see it later on what I mean by that. And we have some initial fastening system embedded into the concrete, and that's more for ease of construction than for a permanent function. This is 2010, it's line B1. We can see a flat steel sleeper appears there in this track, and plus an encapsulation that we'll find in the new lines. It's a booting system called Phoenix, and it's side installed around the rail. Profile was high, so the encapsulation was coming up to the top of the track in that case. Sorry for the bad picture there. This is Luas A1, mostly concrete finishes. You can see the picture. And when it's concrete up to the top of the rails, the difficulties are less because the concrete is self-standing by itself, is keeping the rail in place. The challenge comes when you want different finishes, and we'll see what it is. We started using heavier sleepers on line A1. This is a Rida City system. So actually, those sleepers are much more strong, and then they are able to keep the rails in place and control the gauge and cant and the alignment, even without a full concrete infill on the rail sides. That's a picture of the construction. Let's go back now. What we have seen so far is that the Luas was based on few sections of road and rail. Mostly was a segregated system up to Luas Cross City. So it was only a railway, apart from few road junctions. And we experienced some challenges on the road junctions. We measured about 60% of our concrete shoulders on the junctions were damaged about 3 years ago, and we are replacing them at a certain piece, but it is difficult, it's challenging because you're dealing with a light reinforcement into those shoulders. So you can come out with a patchwork at the end of the repair works. Most of them would fail again. So it's not an easy job. And we are trying to keep following this. But ideally, I would have avoided shoulders for the future lines. And those are other pictures of what's happening at the moment on the existing lines. So shoulders, joint stability, road stability, and that's when I was speaking to you about the joint between the road and the rail. The rail is actually something that moves vertically up to 2 millimeters, while the road is stable enough. So you need to compensate between those two different behaviors. And also, as you can see the picture down there on the right-hand side, our wheel is larger than the rail. So when the rail wears down, if there is concrete around the rail, we're gonna crack the concrete, and then water ingress, tow and freeze, and we are getting into what we call a V-shaped crack along the rail. From a maintenance point of view, it took us 4 nights to replace 18 meters of single rail with a lot of people working on it. As you can see, this is the picture taken at that time. So imagine the cost of rail replacement. Not only that, new challenges coming from Luas Cross City. It's a confined construction site, so we had to build Luas Cross City in most of the places in a single track configuration across in the middle of 2 operational traffic lanes, so very narrow construction sites. The alignment is quite challenging, lots of back-to-back horizontal and vertical curves just to merge with the existing environment in the city. And then it will be will be largely a shared running line because of bus traffic in the city center. So actually shared with very heavy road traffic, and that's why we concentrated our attention much more on the railroad joints, trying to import the experience from the previous lines as well. that says we decided to phase the construction of Luas Cross City starting long time ago with a massive international benchmark analysis to see what's being done across Europe, and then trying to import in Dublin the best cases and to test them in real scale tests. I'll go quickly through what we have seen there. There would be we would take half an hour to speak about each of those systems, but I just want to drive your attention towards the key aspects of each system. This is Paris. You can see they use sleepers as well, B-block sleepers, and filler blocks around the rails. Instead of using the thin encapsulation that we would have used in Dublin, they use those recycled rubber filler blocks, which are quite short. So there is an issue there. And the issue would be stray current. We have a very high requirement in Dublin for stray current leakage from our rails that would transport the current back into the substations. We have a 10 ohm kilometer requirement, which is much higher than the Euronorm standards. And a system like that would probably fail our stray current tests. Now, I have to say, we haven't tested it, but because it's made of very short pieces joined together, the probability of leakage of stray current would be very high. On top of that is a very flexible filler around the rail, and we'll see it in other networks, and we have experienced by traveling around what that means in terms of stability of the road rail joint as well. But probably the light rails in Paris are mostly segregated, and in the few road junctions what we notice they have to use a steel plate on the back of the joint. So it's quite convoluted, very additional bits and pieces to preserve the stability of the joint itself. Berlin, it's even easier, and it follows pretty much a similar system as Paris, and you can see they use those filler blocks, and there is a small encapsulation on the bottom of the rail. The function of that would be to provide the correct elasticity of the track itself under vertical loads. The lines in Berlin are also mostly segregated from traffic, so they use an unreinforced slab, and they induce cracks every tot meters, and they use a low profile of the concrete, so the concrete is stopped at the bottom of the rail, so it has only a vertical rail support function, not lateral support, because they use very strong sleepers for that. Bottom rail continuous pad, as I told you before, Ragon filler blocks type, and the Rita sleepers. And then the rest is all asphalt up to the top, so about 160 millimeter of asphalt. But sure, those tracks are very rarely shared with traffic. Freiburg is actually one of the easiest system, and instead of using sleepers, they use those cross tie bars, which are bolted on the web of the rail. And then they use our similar system, which is the Phoenix encapsulation, the thin encapsulation around the rail. That's the construction in Freiburg. Zurich, which is one of the most interesting systems, I'd say, and they do it themselves, so is internally developed. It's one of the most complex, and I'd say I personally think they ticked all the boxes on in terms of durability and efficiency of embedded track system. It's based on concrete, so all the green layers are concrete, really. So concrete comes up to 40 millimeters shy of the top of the rail, and they only leave the top part to the asphalt. To control the plasticity of the asphalt, they only leave it 40 mil. Plus, you can see there are two joints on both sides of the rail, which is epurable, either bitumen-based or it's similar to rubber joint, really. And then they have an additional fastening device, which is a proprietary system invented by themselves that links the rail directly into the first slab. It's a very stable system, and that's the finish aspect. You can see they share the light rail lines with buses, and there is no problem at the joint. Actually, they don't provide any concrete shoulders, but that's based on 40 mil asphalt only. So the deformation of the asphalt and the compaction is much less significant than what we would get if we had 100 or 160 millimeter of asphalt there. This is Edinburgh. I'm just mentioning Edinburgh because it's famous to have been quite challenging from a track point of view. This is Princess Street after the installation of the first track. You can see the joint there. They used very flexible C-shaped filler blocks around the rail and then full asphalt on top, and that's what they got to. So the repair works are at the bottom there. They had to transform the entire asphalt into concrete to just keep the stability of the joint itself. It was quite challenging actually. They had to redo it twice, I think. This is Croydon filler blocks, but this is segregated. You can see the use of sleepers as well, the reader sleepers. There is no encapsulation around the rail as it appears to be. Bergen, this is the line prior to the last, I think there is the phase 3, the one where Mott MacDonald from Dublin was involved in. So that's the previous line. They use the CDM filler blocks around the rail, supporting the rail from under as well. So there is no differential stiffness between the side of the rail and the bottom of the rail itself. Low shoulders, you can see there are a bit of concrete around the rails, and that proved to be very challenging in terms of joint resistance and gauge control of the track. We measured there, when we went there the last time, there was a significant back flange contact on the inner rail on the tight curves without significant wear on the outer curve, on the outer rail. That meant that there is a gauge spreading when the tram is passing, due probably to the high flexibility of the blocks, and there is no mechanical gauge control between the rails in that case. That's Nottingham, that was built as Luas in the initial lines of the Luas. That's probably where we took it from, because the original lines in Dublin were built on the base of UK experience mostly. This is Nottingham, the new line, the latest one on the south side of the station. It was built with a proprietary system. It's a slip-formed slab track. It's an Alstom system called the Happy Track. So the slab is slip-formed by the machine, and then the machine automatically inserts the direct fixation fastenings, which are Nabla type, into the slab. Now you can imagine the level of accuracy you need to have for the machine to lay the right level of the slab, and it's very difficult to regulate the levels, and especially to provide a specific complex horizontal and vertical alignment. We thought about that for Dublin as well, because it promises to be a very quick system for installation, but our alignment in Dublin for Luas Cross City was extremely challenging. This is a section in Rome city centre of an extension of a tramway there, and they also used quite an old-fashioned slip-form system. Again, we could call it an Happy Track of the previous age, and that's based on slip-forming several sections of the slab and then inserting the direct fixations. You can see the rolls down there are the bottom profiles for the rail to support the rail with the correct elasticity. And this is the design of that. I have to say again, I went there recently, and the joint is extremely problematic. We are having collapse of the asphalt layers all around the rails. So that's something that demonstrates how difficult it is to get that piece right. Again, sorry, you can see from the drawing they used rubber fillers around the rails. This is Florence. Sleeper-based system with our encapsulation that we use in Dublin as well, the Phoenix, that's the design, and full light asphalt. So really that's asphalt from there onto the top, but again those lines are rarely shared with traffic. And that's Karlsruhe. It's a different system. This is a Nedilon system with precast track panels with a slot in, and the rail gets inserted into the precast, and then with this pourable resin, which is Corklast in this case, the rail gets blocked into the slot. We have seen that recently in Heilbronn as well, with the addition of filler blocks as well, and sleeper control for the gauge. And just last week I was in Utrecht, and that's what they're doing there. So it's a further evolution of the Edinburgh system, embedded track. Whereas they use, you can see the bottom on the right, they use those very light filler blocks in foam, and a different profile for the bottom. And then they pour concrete around, and the foam only creates a slot. Then it gets cut away, and you can see that's the finished aspect. So the only foam that remains around the rail are those two blocks, and the rest is a pourable resin around it. And that resin has the function of keeping the gauge and the control of the rail stability. So again, no mechanical fixings. It's resin and filler blocks fixed into the concrete. Precast systems would be a completely different families, and they use them quite often on straight lines in Paris, for example. Now, I know there is a lot there. What I try to do is to say what are the main groups of embedded track systems. And I could say we could group them from the gauge control point of view. So we could have active control or no active control. We could group them from rails fixation and protection. So thin encapsulation, resins poured on side, or filler blocks around the rails. Or we could look at a concrete slab. How high is the slab? Is it only supporting the bottom of the rail, or is it going up to the web of the rail, or is it going up to the top of the rail? That makes a big difference. And then from that also, what is the joints and the finish system? What kind of asphalt is used? Is a polymer-based asphalt? Is a hot rolled asphalt type? And that pretty much depends on what kind of concrete slab levels we are getting. And from the concrete slab level, you will also have to decide what rail fixation, because if the concrete is very low, you want to have a mechanical system to fix the rail in place. So those four families are not so much independent as they look like. They're all interrelated, and depending on the different cities, just as an example, in Germany, every city follows a different standard. So not only there is not a national standard, but there is not even international standard, but there is not even a national standard. The only ones that I'm aware of that are trying to standardize these systems are the French at the moment. And just to give an idea, and then I'll step into what we have done in Dublin, because this is all the background information. So for example, from a gauge control point of view, if we are speaking about mechanical gauge control, we need sleepers. And those sleepers could be Rida, Satiba, Rainfeather. Those are all manufacturer names or others. And those are some pictures of the different sleepers type. If we want to go for an indirect, what I call indirect gauge control, then it means there are fasteners, but there is no sleeper. So it's a direct fixation into the slab track. And you can see the Zurich case, as I said before, or there are different Nabla, Pandrol, Voslo fixations. And then it could be either a top-down technology, whereas you keep the rails in place and then you pour concrete, and the concrete will embed the fastening system from the bottom. Or you do the other way around, you put the slab itself and then you chemically anchor the fixings into the slab. But then the precision and the leveling would be different in the two cases. Finally, there are the cases of no mechanical gauge control. There are no fastenings, there are no sleepers. Then you're either embedding the full rail into concrete through a thin encapsulation, which is pretty much what we have done originally on Luas in Dublin. And you can use Phoenix, Vector ALH, or other system, booting system as we call them. Or you go for filler blocks that we have seen, for example, in Bergen or in Berlin. In Berlin, they go together with sleepers, so this wouldn't be exactly this type. The non-mechanical gauge control and filler blocks would be the case of Bergen, where you really fully rely on the gauge control on the blocks for controlling the position of the rail. Then any manufacturer has put in as much fantasy as possible, and they are promising, good stray current resistance. Probably a very good noise and vibration control with different systems dealing with the rail, with the web of the rail, with the top of the rail, with the bottom, adding or not adding control of the gauge with fastenings. So that's the difficulty for a light rail engineer, is trying to get around what is difficult to understand, what is difficult to envisage for your own system, because a system that is working in a city may not work in your city for different reasons that you can't control. And then the world is at the moment full of turnkey manufacturers that would provide you with a proposal that seems to work in other environments but wouldn't necessarily work in your environment. And getting around these, trying to limit the risks in a design and build environment, which is the environment we're working in TII, is extremely challenging, I'd say. Okay, yeah, I'll jump that. Let's come back to Dublin. I'm conscious of the time that is tight. So we had to fix some targets for us. The stray current is definitely one of our targets. Very high stray current and vibration control limits. So we wanted to go for a continuous encapsulation rather than for filler blocks, because of the concerns with stray current and because of the concerns with the road stability, the stability of the road rail joint as well. The fact that our lines are in several cases, and especially Luas Cross City, share running for about the 30% of the city center section, also pushed us towards avoiding filler blocks for the stability of the joints. Then we had to learn the lessons from the previous lines in terms of the problems with the concrete shoulders around. Plus, we had to look at the construction support to get the construction as quick as possible, and therefore we wanted to control the gauge, the levels, and the alignment already during construction before pouring concrete. Therefore, we thought that the sleeper-based system would give us not only a containment of the alignment during the lifetime of the infrastructure, but especially during construction of the lines. Track and road, that was the key aspect. How do we design our slab track? Is that a track or is it a road? Actually, it's both of them. And if you look at the two requirements, probably the road requirement is the strongest one. The loads coming from the road are higher than the loads coming from the tramways. So the decision was taken to design the slab as a reinforced track slab according to the design manual for road and bridges. And plus, we had to take into consideration the constructability in narrow construction sites in the city center. We went into using the NRA DMRB standards HD 2526 pavement and foundation design with a design life of 60 years for the structural part of the embedded track. And the slab is designed as a continuously reinforced concrete pavement rather than a concrete base. That's because not only we are overlaying layers of asphalt, but we are also using granite sets. And therefore, the only way to go was a concrete pavement design. To increase the rail and road stability, initially we wanted to avoid concrete shoulders around the rail. So our initial idea was, let's implement something that we think is as similar as possible to the Zurich approach, whereas we have a very thin layer of asphalt, joints on both sides of the rails, sleeper-based system that tomorrow we can still sew cut around the rail, access the bolts and reuse them for fastening the new replaced rails inside. And actually we did that on several road junctions on line A1 to City West, and it's still performing very well. Those are two pictures taken at different times. You see the stability of the rail joint, and that's probably due to the very thin layer of asphalt that was used there. That's the construction of the joint itself. It's a bituminous based. In 2013 then we carried out a real scale track test in Red Cow, where we tried to import as much as possible all the experiences that we took from the European experiences, I'd say, and from Dublin as well. And we tested over a 5-meter long single track section, 2 different types of asphalt and 2 different granite sets arrangements, 2 different joints of the road to rail joints, and different arrangement of the slab itself on a sleeper-based system. Just to see, we knew some of them would have failed, but we wanted to check how the behavior would have been. And there were people asking us, is that the new line going to Clondalk? And we had to answer that no, that was only a test track. And that's the information we gave them, testing underway for innovative approach. Actually, we used the parts of the results of this test to inform the design of the first track of Luas Cross City. These are details of the without shoulder configuration on the 2 asphalt section in Red Cow. The first LCC track actually was the one built for the Rosiacket Bridge 2 or 3 years ago now. This was entirely developed and designed in TII with internal resources, and even the alignment of the bridge is the alignment of the bridge itself is dictated by the alignment of the Luas and the navigability, resulting in a very shallow bridge deck. Those are the 2 track types that you can see. The granite sets type is a very shallow because it's on the bridge itself. You can see the picture down there. And we reintroduced the thin sleeper system with concrete shoulders on both sides of the rail because of the thin concrete slab below the rail. We had to ensure a gauge control, and those thin sleeper wouldn't have been enough to control the gauge itself. While on the 2 road junctions on the quays, we provided a different system. But at that time, unfortunately, we failed. I wouldn't say we failed, but there was a strong negotiation with one of the major stakeholders of the infrastructure itself. And we had we couldn't provide a 40 millimeter asphalt that we would have wanted over there. So we ended up in a compromise arrangement. And that's probably the challenge of our job as well. We're dealing with stakeholders around the Luas lines. We're not the owner of the environment around. And that's the most difficult thing, to bring across concepts that you think would work and to convince people around you that that could be the best idea. We got to something that was a compromise. As you see, the asphalt layers are now 2 layers there with the binder and the wearing course. And those 100 millimeters were very difficult to compact, I'd say. And that resulted in a joint that wasn't fully successful, I have to say. So at the moment we are dealing with it. We think the compaction was an issue, but also the thick asphalt wasn't probably the best solution over there. That's why when we introduced the Luas Cross City, then we let the contractor free. It was a design and build environment. So the joint venture was left free to design a proper solution for the embedded track within our stringent employer requirements, where we imported ideas like the use of the thin sleeper, the use of the thin encapsulation that would stop, as you can see the bottom picture here on the left hand side. The new encapsulation is lower, it doesn't get to the top of the rail, and then it's protected by 2 joints, railroad joint that are pourable material. And we also asked the contractor to evaluate whether or not to provide shoulders around the rail. And the contractor approach was that for a safer approach, they provided shoulders. But then at that stage, we then negotiated the width of the shoulder and the design of the arrangement of the reinforcement into the shoulder. That's the final result of a long period of design together, collaborative design, I'd say, with the contractor of Luas Cross City. You can see the shoulders are now 190 millimeters wide as opposed to 150 millimeters, which was on the original Luas lines, to be stronger and also to be able to withstand to maintenance activities. So in this case, the idea is that we can slot out the rail from the shoulder concrete and yet preserve a key structural part of the shoulders for then putting back the rail in place and pouring a grout in between what's left of the shoulder and the rail itself. Also, the use of the sleepers with a protective cap on top of the fasteners would let us in our design exposing those fasteners again for rail replacement and reusing the clamps, the clips that are there. What we can't do today with the original lines because there wouldn't be clips really. The other innovative idea was, you can see the single track is only 2.2 meters wide, the slab itself. And that was a push to try and compact the construction, as I told you before, within very narrow construction sites. To get there, we had to chamfer the 2 edges of the slab track itself. And those are mainly when we are adjacent to a flexible pavement. Then the idea was, you can see it also on the bottom for the granite sets, the idea was to just have a single type of design. But the chamfer edge really was brought forward because of the flexible pavement to avoid differential cracking at the joint with the asphalt pavement. An additional innovation, I'd say, is the use of the pourable rubber filler on the 2 sides of the rail. This would have been the one that emerged from the test we have carried out in Red Cow, is the Edilon STP 75. Which you can see across Luas Cross City. Those are some of the examples of the finish aspect of the shoulders. Shoulders would be exposed aggregate for skid resistance. And the levels are fundamentally here now. The relative levels of the shoulder and the rail are quite important. And we can see that there were some issues in some areas. We are now dealing with the contractor to try and address them in a very collaborative environment. But this infrastructure was actually, I'd say, so innovative from a embedded track point of view that we were able, together with a big effort of the contractor, to deliver an embedded track system across the city of Dublin, about 3 kilometers of double track in slightly more than 1 year, with the entire traffic management, which was a big part, a big challenge of the construction of Luas Cross City. So that's quite impressive in terms of construction times, including crossing O'Connell Street, Abbey Street and Marlborough Street with very complex flange running crossings and turnouts. And actually those 2 crossings were built across the last summer in 4 weeks, as opposed to an initially planned 2 months. Those are some pictures of the construction of Luas Cross City. So you can see on the upper left hand side is the sub-base layer, which is C8, C10, so a light concrete. And they are placing now the reinforcement for the slab, including the stirrups for the shoulders that are all fixed together. Then the rails are inserted in the middle, supported by the thin sleepers that would have some spindles to regulate the levels. And the cages, all the reinforcement cages, are linked directly to the rails, so that the relative height of the hooks of the shoulders and the rail are fixed, because we need a cover of 50 mil over the reinforcement of the shoulder for the durability of 60 years of the concrete and for the exposure class. And we can't have less than 50 mil, but we can't have more than 50 mil, because if we get more than 50 mil, we would have the shoulder almost unreinforced, and the risk of shrinkage crack gets in. So the accuracy of construction of the relative tolerances of the rail and the civil construction was extremely high. Now, as we often say, building an embedded track through the city center is building a civil design with mechanical tolerances, and that's the biggest challenge that we found with the contractor. So those are some other pictures of the construction. You can see the formworks for the shoulders pour, and then pouring the Edilon joints on the bottom left, and finally the finishes, in this case is asphalt on the bottom right. Some of the issues that we found out during construction, for example, you can see the level there of the longitudinal bar of the reinforcement in the shoulder in some cases was too low, just because the relative tolerances of the levels of the hooks in relation to the rail were too low. We ended up with a low reinforcement in the shoulders that may have caused some shrinkage crack. That was locally dealt with, and with a strong quality control on site, we dealt with that on a daily basis with the contractor. Some chipped edges of the shoulder during construction because of the 90-degree sharp angles instead of chamfered angles. That was another discussion we had. The other problems, other issues that we face is the relative levels of the shoulder with the rail. Just to give you an idea of the complexity, in this case we were about 2 centimeters higher than the rail instead of being flush with it, and all of a sudden we can see that traffic running over would chip the edge of the concrete. Again, we're looking at some solutions together with the contractor there. But that prompt, and that's the reason why I have the blue arrow there, that prompted then a different arrangement of the shutters for the pour of the shoulders. So it had to be anchored down, because the problem was found that it was floating up when the concrete was being poured, and therefore we ended up with higher levels. So those are things that unfortunately you learn on the way together with the contractor, and just because there are no standards, and because every time we introduced a new system, that was the first time we introduced it on the Luas in Dublin. But having said that, I think we have achieved a very good construction quality for Luas Cross City that is mostly dealing with all our employer requirements and all our targets, initial targets. That's a very good finish, shoulder flush level with the joint and the rail. Those are some other pictures of the complex construction. This is Stephen's Green with a turn-back facility curving into Dawson Street. And those are some pictures of the finishes there, granite sets and asphalt. For the granite sets, we went for 120 millimeter deep sets for sets stability, although the granite sets area would be segregated from traffic, but there could be occasional emergency vehicle running over. And that required a pocket which is 160 millimeter deep between 120 of the sets plus 40 mil bedding mortar. So the pocket in the forefoot, as we call it, between the two rails would be deeper for granite sets than for the asphalt, which is only 100 mil. And this is the only difference, I'd say, between the two types of finishes on the embedded track. Again, nice pictures in front of the Trinity College, and that's once again Dawson Street. I would have finished the presentation on what has been before and during Luas Cross City construction, and as I say to you, this presentation was mostly dealing with embedded track and the development of the ideas associated with embedded track. If you have any question, I'll be happy to answer.
If you have any questions,
Thank you.
Could you just use the microphone, because this event is being webcast, so the people on webcast can hear it. If you have any questions, could you raise your hand? Any questions?
John McGowan here. I'm interested, given the low axle loading you mentioned, how often do you have to actually change the rails, and is that only where they're running flush with the surface? In other words, the particular one with the groove rolled into the rail. Thank you.
Yeah, thanks for the question. It's an interesting question, actually. We're just coming to that problem as we speak in those days. I think there would be different answers anyway, but to make it short, on the straight section, we think that the life expectancy of our groove rail will be in around 25 to 30 years. So that's not a big challenge in those cases. While on the tight curves, on the tight bends, we are already into maintenance limits. And we started already rail replacement for the lines that were built in 2004. So I'd say on the tight bends, with the rail hardness that was used on the original Luas lines, the life expectancy is about 12 years, I'd say. Now, what we have done for Luas Cross City on the tight bends, we have increased the hardness of the rails to extend their lifetime. And we have also used a low carbon steel for those rails, making it possible to weld repair the rails. So instead of replacing them, what we would expect is that we can deposit, weld, and reconstitute the profile of the rail at least one or twice before we have to replace them. So if you think about it, we'll expect on the Luas Cross City, I would expect that I can retire before having to replace the rails in Luas Cross City. But I may be too optimistic. I may be optimistic.
Any more questions?
Brona Lennon here from McDonald. Just with the positive outcome of the test track of the grass on the slab track, is there any intention to carry through with that and put it on the slab track?
Not at the moment, unfortunately. We don't think we're going to retrofit the existing slab track into grass track. It could be in the far future, but there is no funding at the moment allocated for that work. So the real reason why we did that test is to have a typological grass track for Dublin in the future. And actually that test was carried out to check the stray current resistance of the track and the mechanical and resistance to vandalism of the various parts, because there was a feeling that that track would have been prone to vandalism, which were all successful. So we have it in the pocket for future lines in case we need to build grass track. That just didn't come for Luas Cross City because there is no grass track sections there.
Marcello O'Warren, have you done any analysis on the differences in the different fixing systems on corrugation?
So you mean if we have checked corrugation development on the various systems? We haven't done a specific analysis, as you know probably. We haven't done a specific analysis. My feeling, and it's a good feeling now, it's that we are having more corrugation on the slab track, far more than on the other track types. First of all, for corrugation we mean it's a wavelength deformation of the top of the rail that then gives rise to noise and vibration. And it can only be tackled by grinding the surface of the rail, which we are doing on a constant basis. The slab track is developing more corrugation because of the way the fixings are working, and we find a different wavelengths after each fixing. And unfortunately the Luas is more prone because of the constant axle load and the constant speeds which we are negotiating each section of the track. But sure, the slab track is the one that is more prone to that. Ballast track, I'd say, is the second, but that's also due to the speed. You need to be able to decouple. What is the speed the speed part of it and what is the alignment or the track installation part of it. And I think the speed is playing a big role in that the speed is higher on ballast track and slab track as opposed to the embedded track. Another place where we are confronted with the corrugation, as you probably know, is acceleration and braking in the groove rail, so embedded track before and after the stops as well. I don't know if I answered your question. Not scientifically though.
Any more questions?
Cormac Bradley from RPS. Marcello, you talked about the fact that it's got to the stage that you don't even have a national standard for the various types of tracks. And in the examples of the locations that you visited to show different types of construction and slab construction, will the work in Dublin lead to any sort of international agreement, or is it just an ongoing, well, each country or each city will do what they do, or is there now a consensus as to what's the best way forward in terms of generating a national or even international standard?
No, I don't see that happening, unfortunately. I mean, unfortunately, at least we'll have our job forever, you know, because if there was a standard, you just apply the standard. Jokes aside, no, there is no way we can get to an international standard. And actually, whenever you speak with one of the manufacturers, as I said before, each one of them is telling you that his wine is the best for sure, and it ticks all the boxes. And then actually when you go into the details, you'll see that something is done, something else is not done. So there is no standard and there is no way you can standardize light rail, also because it mostly depends on the finishes and the architectural requirements and the landscape and hardscape requirements of every city. Some cities give more importance to the noise and vibration protection. For example, if you go to Germany, they care probably less about the visual aspects of the light rail infrastructure. If you go in Stuttgart or in Frankfurt, you step out of the main station and you'll see there is ballast track in the city center in front of the main station. They are very functional but less caring about the aspects. If you go to France, they are much more looking after the aspect of the. We took from France, I'd say, our landscape and our hardscape requirements on the Luas. But then so many different players are playing around it that it's almost impossible to standardize. It's still quite difficult to standardize heavy rail from a signaling point of view. For example, the ERTMS is still under discussion in Europe. So, and I'd say it's much easier from an insulation point of view because the heavy rail is insulated from all the rest of the environment, while light rail is urban related. And that's why, to your first question, whether or not Dublin will influence the development of embedded track, I'm trying my best going around and presenting what we have done. And I think we are achieving very good results here. I'm not sure whether it will influence the development of light rail track systems.
Any more questions? Can I ask Kevin Sheridan, on behalf of all the hosts here this evening, to extend a vote of thanks, please. Kevin is chairman of the Institute of Civil Engineers in the Republic of Ireland. Thank you.
Thanks very much, Michael. On behalf of Engineers Ireland, Railway Group and Civils Group and the Institution of Civil Engineers, I'd like to propose this vote of thanks for an extremely comprehensive and very interesting talk in this area. And I would like you to show your appreciation in the normal way. Thank you.